Hello everyone! It is a pleasure to participate in the ICMSN 2026 conference. My name is Dovile Petrauskaite and I am a master's student at Kaunas University of Technology and a specialist at the Lithuanian Energy Institute. And today I will present my postdoc titled Strategy Development for Valorising Byproducts Generated During Burning Landfill Waste to Produce Eco-Friendly Building Materials. So landfills are one of the most persistent environmental challenges worldwide, and even after closure, old landfills continue to emit greenhouse gases such as methane and carbon dioxide, and their leachate can contaminate soil and groundwater, and across Europe, landfill mining projects are emerging to recover materials and energy, also to reduce emissions and reclaim land. So when landfill mined waste is incinerated, it produces a byproduct similar to municipal solid waste incineration bottom ash. And this ash is rich in calcium, silicon, and aluminum compounds and has a crystalline structure that makes it potentially reactive. So instead of treating it as a waste, we could explore its reuse as a secondary raw material in construction, also supporting circular economy goals and reducing the demand for virgin resources. And the European Union directives are limiting landfilling to 10% by 2035, which basically means that valorization strategies like this will become increasingly important. And my research contributes to that direction by examining how landfill-derived ash behaves when it's incorporated into binder systems. So when we study waste-derived materials, understanding their microstructure helps us predict whether they will behave like traditional binders or need some kind of a modification. And the aim of this study is to investigate whether landfill-derived ash could be incorporated into sustainable building materials and how its microstructure changes when it's used as a binder replacement. So in simpler terms, I wanted to see if the ash reacts with other components, forming new hydration products, or if it mostly acts like an inert filler. So understanding this helps predict its potential influence on strength and durability. So for this work, I prepared samples where 5% and 10% of the binder was replaced by landfill-derived ash, and the binder system itself contained metakaolin and calcium hydroxide. So after 28 days of curing, the samples were sputtered with gold to make them conductive, and then analyzed using scanning electron microscopy coupled with energy dispersive spectroscopy. So SEM allows us to observe the morphology, the shape and texture of particles, while EDS provides elemental composition maps. And together, these techniques reveal how the ash interacts with the binder and whether new phases form. So magnifications ranged up to 40K, which is sufficient enough to distinguish crystalline hydrates from amorphous gels. So let's start with the 5% replacement sample, and the SEM micrographs show plate-like crystals surrounded by gel-like material, and these plates are consistent with AFM-type layered hydrates, aluminoferrite monosulfate phases, while the surrounding material corresponds to CaSH gel, the main binding phase. So this indicates early pozzolanic activity. Of course, some unreacted particles are still visible, suggesting that the reaction is still partial at this stage. And this morphology implies that the ash participates in hydration, but not completely. It contributes both as a reactive component and as a filler. So in the 10% replacement sample, the microstructure becomes more pronounced, and we can observe needle-like crystals typical of AFT phases, mainly yttringite, along with more extensive CaSH gel formation. And this suggests stronger interaction between metakaolin, ash, and calcium hydroxide, leading to more complete hydration. So this richer microstructure could enhance material strength because the gel fills pores and binds particles more effectively. So the transition from AFM type plates to AFT type needles reflects the evolution of hydration products as the ash content increases. And EDS mapping also supports these observations. In the 10% sample, the distribution of calcium, aluminum, and silicon is more homogeneous, indicating better mixing and more complete hydrate formation. And the spectra show strong calcium and silicon peaks, moderate aluminum, and also traces of iron, which is consistent with pozzolanic reaction products. And importantly, no heavy metals were detected in either sample, which is pretty encouraging for environmental safety. And a slightly higher carbon content was observed, likely originating from organic residues in landfill-derived ash. So carbon in these ashes could appear as inorganic aluminosilicate structures combined with organics or carbon-based molecules. It could also be carbonates or even elemental carbon particles. While excessive carbon may slightly reduce the pozzolanic activity, it could also improve thermal insulation and reduce the density, which may be beneficial for lightweight materials. So also further standardized leaching tests are recommended to confirm long-term stability and environmental compliance. And it is also very important to note that the landfill-derived ashes are not uniform materials at all, and their composition strongly depends on the age of the landfill, the types of waste deposited, also from drilling depth and the incineration conditions themselves. And for example, ash from older landfills tends to contain more carbonaceous residues and unburned organics, while ash from newer sites may be richer in silicates and aluminates. And these differences influence both the reactivity and the environmental behavior of the material. So in future work, comparing ashes from several landfills could help identify which waste streams produce the most suitable byproducts for construction applications. So what do these results mean? So the coexistence of AFM and AFT phases together with a CaSH gel basically demonstrates that the landfill-derived ash is not really inert, and it participates in hydration reactions. So this pozzolanic behavior could improve strength and durability while also reducing the amount of conventional binder required. So from a sustainability perspective, using landfill-derived ash could help us close the loop in the waste management because we recover materials from old landfills, also reducing greenhouse gases at the same time, and also creating value instead of disposal. And it also aligns with the European Union's circular economy goals and also supports the transition towards low-carbon construction materials. So overall, these results indicate that the landfill-derived ash could participate in pozzolanic reactions and act as a filler, and it supports its potential use as a secondary material for more sustainable construction. However, further characterization is needed, including X-ray diffraction, FTIR, a thermogravimetric analysis, and also mechanical testing to quantify the phase composition and also strength development. And the future work will also focus on leaching behavior and long-term durability to ensure environmental safety. as well as on a comparison of ashes from waste of different landfills. So thank you very much for your attention, and I look forward to any questions or discussion during the conference.